For this lesson, we're going to be taking a look, actually again, revisiting the topic of the slope of a tangent line. And in particular, we're going to be adding this new idea. It's not entirely new. We've talked around it, but we're going to be coming at it a little bit more directly in this lesson and some lessons going ahead, which is this idea of something called a limit. So just as a quick review, if I want to know the slope of the tangent at P, so that would be if I want to know the slope of this red line. Up until now, all we've been able to do is approximate that. At least in most circumstances, we've only been able to approximate it. And the way that we've approximated it is by making use of the idea that I can always calculate the slope between 2 points. And so I can estimate the slope of this red line by choosing some other point on this curve, on this function. So you can see if I choose the point Q1, that's not a very good estimate of the slope. But as I choose my point to get closer and closer to my value of P, so for example, if I choose the point Q2, that's a better estimate. Q3 is a better estimate still. And I could eventually choose a point that's actually very close to the point P. And you can see now the red line appears to go through that blue point. It wouldn't go through exactly because that's still an estimate. But the idea here is that as I get closer and closer and closer, as I bring that point in even closer still, my estimate's going to get better and better. And so we've been making use of that idea when we've looked at rate of change in the past, and we're going to continue to do so, but we're going to extend it a little bit further this time. So speaking of rate of change, when we talked about rate of change, we talked about different types of intervals. We talked about a preceding interval, a following interval, and a centered interval. And we established that in general, we want to use what's known as the following interval. So if I want to know the rate of change at some value x equal a, then what I do is I actually also look at my second point, which is going to be a little bit further than a. So I add some small value h. And as we discovered, the smaller my value of h, generally that means I'm going to get a better estimate for my slope of the tangent. Ideally, we would like that value of h to be 0, but we can't divide by 0, so that causes us a problem. So all we can do is make that as small as possible. But there is an idea in mathematics known as a limit, where we can actually say, okay, I want to consider what happens as h approaches 0. And as I mentioned before, when I just started the lesson, we've talked around this many, many times. We've talked about the idea of approaching, for example, dividing by h or dividing by 0. We've talked about, well, what's happening as I get close to an asymptote? That is still a discussion of a limit. You're asking what happens in the limit as I get close to an asymptote, to a vertical asymptote. Or what happens as I go to plus infinity or minus infinity. So we've dealt with this conceptually already. Now we're just formalizing the mathematics and the representation of it. So back to the idea of this slope of the secant line. As this small value h approaches 0, my slope is going to become a better and better estimate. Ideally, when I actually reach 0, then I have the slope of the tangent line. And so that's why you'll notice I represent this not as an approximately equal to. The slope of the tangent line is the limiting value that comes out of this formula when h approaches 0. And the way we say that is the limit. So the way we read this, the limit as h approaches 0. So let's put this into practice. So you can see I've got just a simple quadratic, as simple as you could get. And here I have I've shown the graph of this very simple parabola, and the dotted red line represents my tangent line, and I want the slope of that line. But the way that I'm going to do this is I'm going to use this idea of a limit. Now, what we're going to find out here is that because this is a polynomial, we're always going to be able to use the limiting idea. So first of all, I'm just going to rewrite this as f of x equals x squared. I'm going to remind you of what we had on our previous page, which is the slope of the tangent is the limit as h approaches 0 of f of a plus h minus f of a over h. So what we want is when x is equal to 3. That's the same thing as saying that my a value is equal to 3. We're trying to find the limit at x equals 3. So my slope is equal to the limit as h approaches 0 of, and so it's going to be f of, and instead of a plus h, it's going to be 3 plus h minus f of 3 divided by h. And we don't need to know what h is. We don't need to give it a value. We've done that in the past where we've actually assigned a value. But we're going to keep working through the algebra here. The limit as h approaches 0. Now, I will warn you right now, some people find this quite tedious to write out the limit as h approaches 0, the limit as h approaches 0. For each line here, you have to include it. If it gets so bad for you, then you could go off to the side and you could do some rough work where you actually develop f of 3 plus h minus f of 3 over h. You could do that over here in rough work if you wanted to. But otherwise, you can't just drop the limit and then have it reappear. So what is f of 3 plus h? That's 3 plus h all squared, because f of x was x squared. Minus f of 3 is just 3 all squared divided by h. And that is the limit as h approaches 0. Now 3 plus h all squared, I just square that as a perfect square binomial. So that's going to be 9 plus 6h plus h squared. I don't need these brackets. I'm just putting them there to show this is my f of a plus h and minus f of a, or in this case minus 9, all divided by h. The limit as h approaches 0. So now I recognize, okay, this is positive in front, so I didn't really need this bracket. I've got 9 minus 9, which is equal to 0. So all that's left in the numerator is 6h plus h squared over h. And this is, I mentioned when we started this, I said one of the properties of a polynomial is that this will always work out that we can take the limit as h approaches 0. Because right now, if I try to imagine h equal to 0, well, that's dividing by 0. And I can't imagine that. I don't know what that means. But I have common factors here in the numerator. I can actually factor out the h, and I end up with 6 plus h divided by h. I'm going to divide out the h's and replace those with 1. Now we know that, of course, that means that h cannot be equal to 0. But I'm not setting h equal to 0. I'm saying what happens when h gets close to 0. So this is the limit as h approaches 0 of 6 plus h. But what is the limit as h approaches 0 of 6 plus h? And it quite obviously is equal to 6. So the slope of my tangent line in this case is equal to 6. It is equal to exactly 6. This is not an estimate. It is exactly 6. Okay, we're going to carry on, same example, except for you can see I've changed the function, which means it changes the graph. Obviously, it's going to change the slope. So carrying on with what we did in the previous example, whenever possible, we want to change the expression algebraically so that we can get rid of h as it appears in any denominators. And if we can do that, if we can get rid of the h from all denominators, then we can evaluate the limit exactly. So once again, just to remind you, this is f of x is equal to 6 over x. So my slope is equal to the limit as h approaches 0 of f of, and now this would be a, but we know that's 3 plus h minus f of a, but we know a is equal to 3, divided by h. The limit as h approaches 0. What is f of 3 plus h? Well, f of x is 6 over x. So f of 3 plus h. And you want to be really careful here. I'm going to put in my main dividing line. This is over h. So f of 3 plus h is simply 6 over 3 plus h. Wherever there was an x before, I've now put a 3 plus h, minus 6 over wherever there was an x before, I'm going to put a 3. So we have the limit as h approaches 0. This first one, again, I'll put in my dividing line. 6 over 3 plus h is just going to stay the same for now. Minus 6 over 3 is just minus 2. The limit as h approaches 0. And now I need to, again, that's not very good. Over h. Let's get a common denominator for the numerator, which is going to be 3 plus h, because this is 2 over 1. So that's just going to become something over 3 plus h. This already has that denominator, so the 6 just stays the same. Minus 2 times bracket 3 plus h. It's so important when you're doing this to make sure you're keeping track of what fractions go where. You can see that's why I'm being extra careful here. So I'm putting in, this is all over h. And now I've got 6 minus, actually let's put this top part over 3 plus h. I wouldn't normally write this out myself. I'm doing this for your benefit so you can understand each piece as I'm putting it in. And now the numerator of the fraction that's in the numerator, 6 minus, now 2 times 3 is just 6. So that becomes 6 minus 6, which is 0. Actually, let's write it out. 6 minus 2 times 3 is 6. Negative 2 times h is minus 2h. The limit as h approaches 0, 6 minus 6 is 0, leaving me a negative 2h over 3 plus h, all divided by h. I still have division by h here, but I'm dividing by a fraction. I have a fraction over another fraction, so I'm actually going to turn that into a multiplication of two fractions. Negative 2h, all divided by 3 plus h, and that's going to be multiplied by the reciprocal of that fraction, which is 1 over h. But now h goes into h once, h goes into h once, and I end up with the limit as h approaches 0. Negative 2 times 1 is simply negative 2. 3 plus h, all multiplied by 1, is just 3 plus h. Now, if you have a little reservation here, you might say, well, hold on, we still have an h in the denominator, but I want to consider h approaching 0. When h approaches 0, 3 plus h simply approaches 3. So I'm not going to have a division by 0 here, I'm going to have a division by 3, and that's perfectly fine. So I end up with the slope of my tangent is equal to negative 2/3. Which, of course, because I provided the graph using technology, we actually could have discovered that quite easily just by doing a rise over run. And you can see that is negative 2 and positive 3. Negative 2 over positive 3 is negative 2/3. Okay, determine the slope of the tangent line when this is our function. It's the radical square root of x plus 1. So again, f of x is equal to, that does not look like the correct graph to this. It is not the correct graph to this. So what is the square root of x plus 1? Square root of x plus 1 would be here to here to here. Apologies for that. And we want to know the slope at this point, so it's going to be something like that. Alright, so f of x is equal to the square root of x plus 1. And so slope is equal to the limit as h approaches 0 of, I'm tempted to go ahead here, like to take out a couple of steps, but I don't think that serves any good purpose. I'm going to use the exact same opening statement that I used on the previous two. And I just want you to recognize, as you get more comfortable with this, you might have proceeded directly to this step, which is, what is f of 3 plus h? Well, wherever I see an x, 3 plus h plus 1, minus, wherever I see an x, square root of 3 plus 1, all divided by h, and that's equal to the limit as h approaches 0. Now I can simplify the contents of each of these radicals quite easily. 3 plus 1 plus h, so that one becomes the square root of 4 plus h minus square root of 4. The limit as h approaches 0 of the square root of 4 plus h minus 2, we take the square root of 2, all divided by h. Now at this point, there's no way we can do any kind of common factoring here, so you might think, oh, in this example we can't go any further. And sometimes that will happen. And then the best thing we can do, at this point at least in our mathematical knowledge, we would have to do an estimate. But if you recall, a skill that we looked at in the previous lesson was the idea of rationalizing. And you can rationalize the denominator or the numerator. So hopefully this is making clear why we talked about rationalizing a numerator, because I'm going to now take square root of 4 plus h plus 2. I'm going to take the conjugate, 4 plus h plus 2. I'm going to multiply that out, the limit as h approaches 0. Now, be careful when you do this. Square root of 4 plus h minus 2, square root of 4 plus h plus 2, it's going to be square root of 4 plus h all squared minus 2 all squared. It forms a difference of squares using each of these. And in the denominator, I just get h times square root of 4 plus h plus 2. Now, this definitely doesn't look better. It looks decidedly worse. But you're going to have to trust me that I'm taking us in this direction for a good reason. So the square root of 4 plus h all squared is simply 4 plus h. Minus 2 all squared is 4 times h multiplied by this more complicated factor. 4 plus h minus 4. 4 minus 4 is 0. So that's the limit as h approaches 0. 4 minus 4 is 0, leaving me only an h in the numerator. And now we see that that has worked out very nicely, because I can divide out my h's, and because I'm only approaching 0, this is going to work out just fine. This becomes the limit as h approaches 0 of 1 over 4 plus h square rooted plus 2. So what happens when this approaches 0? That just becomes 1 over 4 plus h becomes 4 plus 0. That becomes the square root of 4 plus 2, which is equal to 1 over 2 plus 2, which is obviously 1 over 4. And I apologize for the graph being wrong, but you can see from my quick little hand-drawn version and my estimate of this is what the slope line is going to look like, well, that actually is a pretty good estimate. It's a positive slope, and it's a pretty shallow slope, so a slope of 1/4 seems to make sense there. Okay, and that's it. So don't forget the new algebraic skill, rationalizing the numerator. If you're dealing with something that's a radical, you're probably going to have to make use of that. And also the other thing for you to keep in mind, I always want you trying to algebraically express these so that you can divide out that h in the denominator. That's always going to be your first goal when you're trying to do these. That'll allow you to evaluate them exactly.